Welcome to Lesson 3 of Chemistry. In this lesson, we'll discuss the system chemists use to communicate their calculated results. It is important they use a system so that other scientists can assess the validity of their results. The first thing we will look at are rounding rules. I know you've been rounding since elementary school, but it is helpful to have a rounding refresher, especially since we have to examine rounding from the lens of significant figures. When rounding, always begin by looking at the number from the left. Underline all the number of significant figures you'd like to keep and circle the following number. Let's do some practice so you can see how I would round these numbers to the proper number of significant figures. Since in this exercise we are asked to round to 3 significant digits, notice I've approached each number from the left and highlighted the first 3 significant digits. And the final number, remember that due to the Pacific rule, the leading zeros are not significant. Look at the first example. We've underlined the leftmost significant digits, 5 to 7, and we must examine the number to the right of our final digit. That number is a 7. 7 tells us we need to round up, so we write down the digits 5 to 8. But there's a problem here. 5,277 doesn't round to 528. So this leads us to the last step. After you write down all the significant digits required, you'll have to add placeholder zeros until you get to the decimal place. So when we add the 0 until we get to the decimal point, we get 5,280. 5,280 is definitely an approximation of 5,277. Looking at the next example, you can see that the first 3 digits are 403, and if 4 follows the last digit that we wish to keep. Since 4 is less than 5, we are going to stay, never round down. So our final answer would be 403. 403 is a rounded version of 403.495. In this final example, you can see that after our last significant digit, 5, there is a 3. Again, a 3 means that we stay because 3 is less than 5. So we'll write down the numbers 675, but 675 is not a good estimate of 0.0067532. So here we'll have to add in the preceding place value zeros so that we can give our rounded number a similar magnitude as our original number. The reason we had to review rounding is it's important to remember that scientists rarely report simple measurements in their data, but instead they take those measurements and perform calculations. We want to make sure that our reported answers are no better than our worst instrument. Therefore, there are different rules for different mathematical operations. When carrying out addition or subtraction, our answer should have no more decimal places than the least amount of decimal places in our measurement. So when we look at this addition problem here, what we'll notice is that we have different instruments being used for the measurement of these 3 grams. This instrument is least precise or has the least number of decimal places, so we want our final answer to have no more decimal places than our worst measurement. In this case, we should have no more than 2 decimal places. So we'll use the same rules for rounding that we talked about earlier. We'll underline the digits we want to keep and examine the next digit to determine if we stay or round up. So in this reported answer, we should only report 7.72 grams. In these additional examples, you can see the calculator answer in red. But remember, we must report our answer to the proper number of significant digits. So in the first example, our least number of decimal places belongs with the 21, which has no decimal place, so our answer should be rounded to the ones place. In example number 2, we see that the least number of decimal places is 3, so we must only keep 3 decimal places in our answer. So I'll underline the first 3 decimal places. The 6 that follows those 3 decimal places says we should round up. So here is our rounded answer. It is important to remember that you have to round your answer. You can't just simply truncate your answer by removing the excess digits. In example 3, since 31.3 has only 1 decimal place, our answer should only be reported to 1 decimal place. So our rounded answer is 85.8. The 5 makes us round up. In the final example, we only want to keep 1 decimal place. Since the 6 causes us to round the 9 up, our rounded answer becomes 5.0. The rules for multiplication and division are different than those for addition and subtraction. Instead of counting decimal places, our answer has to have the same number of significant figures as the measurements provided in the work. So when we look at the example question, we can see the number 2.50 has 3 significant digits, while the number 2.8 has only 2 significant digits. When I place this problem in my calculator reports an answer of 7, but 7 does not show the precision that I've measured to the tenths place. So I'll have to add 1 more significant digit. My reported answer should be 7.0. If you have to add significant digits, simply add zeros. Let's look at the 3 examples on your paper. I've recorded the calculator answer to each mathematical operation in red. Now, in the first multiplication example, we see that we begin with a number that has 3 significant digits, and we multiply that by a number that has just 2 significant digits. That means our answer should only have 2 significant digits, so it has no more significant digits than our least significant number. That means we'll keep the first 2 significant digits, and we'll refer to the third to determine how to round. Our answer here would be reported as 12. In the next example, we can see that 589 has 3 significant digits, while 12 only has 2. When we place this work into our calculator, we get a very large irrational number. Our work, though, was not recorded to so many significant digits. So our answer should only be recorded to 2 significant digits. We'll underline the first 2 significant digits and look only at the next significant digit to determine how we round. This answer would be rounded to 49. In the final example, we have the number 4, only 1 sig fig, and we multiply by 78 2 sig figs. That means our answer should only have 1 significant digit. If we want to write the number to only 1 significant digit, we can't simply write 3 because that doesn't show the magnitude. We're going to have to add zeros to show the place value. So our number should be recorded as 300. If you have to add significant digits or remove significant digits, they can always be replaced as zeros. Remember, in the number 300, these zeros are not significant because there is no decimal, meaning we start at the Atlantic side of the number, count through the zeros, and so the only significant digit is the 3. A lot of students struggle with significant figures and calculations. The good news is that in a free response question, As long as your answer is properly rounded, it should be accepted. However, do know that significant digits are rounded in multiple choice questions. Look here at this student's work, where they attempted to apply the heat calculation equation. You can see the equation in blue and the variables in red. When placed in a calculator, the product between these numbers comes out to be 6,270, but that choice is not provided in the multiple choice answers. So you'll have to find the rounded answer that is closest. In this case, that is answer C. The final concept we want to explore is writing numbers in scientific notation. As chemists, we tend to use very large and very small numbers. Writing numbers in scientific notation is an easy way to make sure that only significant digits are displayed and insignificant zeros are eliminated. For example, the distance between hydrogen molecules is very small, but this number can be represented so we can eliminate the insignificant zeros crossed out in blue and rewritten as 3.70 times 10 to the negative 8. While the number of water molecules in 1 milliliter is a very large number. Again, we can rewrite this number by eliminating the insignificant zeros in scientific notation. The basic format for any number in scientific notation is to include a coefficient. The coefficient must be between 1 and 9.9 repeating. And we'll take the coefficient times 10 to a given exponent. If the exponent is positive, it means the actual number is larger than the coefficient. If the exponent is negative, it means the actual number in standard notation is smaller than the coefficient. This relates to significant digits because basically when we write in scientific notation, we write the first significant digit, a decimal point, the remaining significant digits, and then times 10 to the exponent, the number of places we'll need to move the decimal to display the true magnitude of the number. Let's look at this problem where we were asked to write these large or small numbers to only 3 significant figures. The first thing we should do is to rewrite these numbers by rounding them to only 3 significant digits. Remember, when you round, you underline the first 3 significant digits and circle the next significant digits to determine how you should round. In this first example, we are going to stay and we will replace all the remaining digits with 0. Now we can write it in scientific notation. To write a large number in scientific notation, take the decimal point and count the number of spaces you must move it until the number shows between 1 and 9.9 repeating. That occurs as we move the decimal to 7.89. So our coefficient will be 7.89. The number of places that we must move our decimal place will be the exponent on the 10. That will be 11. 7.9 times 10 to the 11th power. In the next example, again, since the decimal is present, we'll start counting significant digits from the Pacific side. We see that our significant digits start with the 3. We'll refer to the 7 for rounding. So when we write this number, we have to include all the insignificant zeros as they are important to show the size of the number. And then 3, 4, and the 7 makes us round up to 5. So to write this value in scientific notation, we are going to move our decimal over until we arrive at a number between 1 and 9.9. That number would be 3.45. So our coefficient is 3.45 times 10, and because this number is smaller than 3.45, it will have a negative exponent. The number of places we move our decimal is 5. Now it is time for you to go to Google Classroom to complete your homework. Come with any questions that you have to class.